Okay. All right. We'll go ahead and get started. Hi, I'd like to thank everyone who is joining us. Welcome to today's CNCF webinar, Kubernetes Security Anatomy and the recently disclosed CVEs. I'm Christy Tan. I'll be moderating today's webinar. We'd like to welcome our presenter today, Gadi Naor, CTO and co-founder of Alside. A few housekeeping items before we get started. During the webinar, you are not able to talk as an attendee. There's a Q&A box at the bottom of your screen. Please feel free to drop in your questions in there and we'll get to as many as we can in the end. This is an official webinar of the CNCF and as such is subject to the CNCF Code of Conduct. Please do not add anything to the chat or questions that would be in violation of that Code of Conduct. Basically, please be respectful of all your fellow participants and presenters. Please also note that the recording and slides will be posted later today to the CNCF webinars page at cncf.io/webinars. With that, I'll hand it over to Gadi to kick off today's presentation. Take it away.
Thank you so much, Christy, and thank you everyone for joining me today. In our session today, I am going to talk about Kubernetes Security Anatomy, and specifically we have a very interesting topic related to the recent CVEs disclosures. As an anecdote, while I submitted the original slides for this talk, we actually had only 2 CVEs as part of this webinar. And since then, there were 3 more CVEs disclosed, which means that this is a great area for anyone that is kind of adopting Kubernetes as part of their cloud native application infrastructure. By way of me hosting you guys today, as far as where I'm from, I'm happily locked down or grounded, I should say, in Tel Aviv, Israel. And it looks like it's going to stay like that in the foreseeable future, unfortunately. Other than doing cloud native fun stuff, I try to enjoy skateboarding, which happily I managed to do that more often than usual because of the new reality. And by way of a professional experience, I spent most of my career as a kernel developer, and in the past few years since starting Alside, which is a pure play Kubernetes security company, which is focused on delivering end-to-end Kubernetes security, I got an upgrade to deal with only the fun stuff, which is containers, Kubernetes, and dealing with building scalable systems and securing them. What are we going to see in this session today? So we are going to start with an overview that kind of takes us to the 4 C's, and which is cloud, cluster, containers, which is somewhat kind of extended to Kubernetes, and code. And we'll see what are the building blocks that you really need to think of when we are trying to build a practice or a thesis around our Kubernetes security. Hopefully I'll be able to show you some demos that are relevant to the topics that I am going to discuss in this session, as well as discuss the recently disclosed CVEs. As I mentioned, there were 5 of them, and also talk about detections and preventions in the context of those CVEs. So without further ado, I'll dive right in. So when we are really trying to think about what are the Kubernetes security building blocks, this is a relatively complex topic. And it's not because Kubernetes is not complex, it's because security by itself is a complex topic. And when we really try to think about what do we want to achieve with improving or implementing security controls around our environments, we really need to think about how we build our clusters, how we access our clusters, how we operate our clusters. And even before that, what exactly are we doing as far as the code that we are shipping into our infrastructure. So let's start with the easy stuff, which we are not going to talk very much in depth in this webinar. It mainly revolves around the first C, which is our code. And when we really think about what do we want to implement as far as our code controls, so naturally we have the traditional practices of scanning our code with code analyzers. There's whole religious around security application testing and dynamic application security testing and software component analysis, which pretty much kind of involves the large challenges or the huge challenges that we have with adopting and bringing in open source components as part of our applications. And once we kind of feel comfortable around the practices that the code analysis brings us, we really want to think about how we package them in containers. So we want to think about container image scanning, and the main motion that we see with the security building blocks that we want to apply in this context mainly revolves around integrated security controls to our development lifecycle and development kind of practices, as well as our CI. But once we move from this point and then think about the Kubernetes environment that we are spinning up, so we really need to think about two more C's. The first one is the cloud.
Hey, Gadi,
yeah.
We can't see your slides. I think there's a delay on your end. Can you check this?
Let's see. Can you see my slides?
Yes, we can now. Thanks.
All right. So I am, for the sake of completeness, this is the entire slide. And right now I am at the 2 additional C's. So we talked about the code, and we really want to talk about the cloud and the cluster. So essentially, when we are deploying our Kubernetes or provisioning our clusters into the cloud, we really need to think about, first of all, how we secure our cloud account. So this is an entire topic by itself that we really need to kind of figure out. How do we provision our Kubernetes clusters? How do we segment them from other parts of our cloud infrastructure or services? How do we regulate access to the users to the cloud account? Because essentially, this is something that can be prerequisite to access our Kubernetes environment. But when we are starting to think about the Kubernetes cluster itself, so we want to talk about what exactly are we doing to secure the control plane, which is the brain of our cluster. And if we are leveraging, for example, managed Kubernetes services like EKS or AKS, then the cloud providers actually takes a lot of the burden from us in terms of securing the control plane and the management plane of the cluster. And we'll see that slightly in depth later. As far as identity, as we try to think about who do we allow access to the cluster. So the first thing we want to make sure is to establish the identity of users as well as service accounts that are accessing the cluster. So here we want to make sure that we have very strong identity controls in terms of accessing the cluster. So we want to have something like OIDC, which pretty much enables us kind of stronger authentication and making sure that credentials are expired in a relatively short time intervals. So we can make sure that users are not able to access the cluster in a relatively permissive way. If you try to think about a little bit of what happened with Twitter, I mean, not that I'm trying to be kind of go in depth there, but essentially there was some social engineering, like human social engineering elements. So if things are breaking through our identity systems, which is what happened with Twitter, think about the blast radius that would happen in terms of your Kubernetes cluster if your highly privileged SRE is performing actions against the cluster. And we will see the relevance of that in the context of the control plane CVEs that were disclosed. Now, once we move from the identity to RBAC, we really want to make sure that as far as authorization, it basically regulate who is allowed to do what. We have the right controls in place, and those controls should first off regulate what users are allowed to do, as well as what service accounts, essentially operators and automated processes that are running from within the cluster and accessing the API server. Validating admission controllers and mutating admission controllers, you can really think about them as extensions to the Kubernetes RBAC policies, where whenever the RBAC policies are not granular enough, or you really want to do some sort of operations that extend those policies, we can really turn into leveraging the extensible parts of Kubernetes, which are in the form of those admission controllers. Once we move from our infrastructure to our workloads, then this is where things become extremely interesting. So we first want to make sure that we run our workloads, our application workloads, and those can be also our infrastructure workloads in the best secured manner, in the sense that we do not want to run anything privileged. We want to make sure that we don't create services of type load balancer that enable access into the cluster. We want to make sure, for example, that if we expose the cluster to the outside world, or we want to make sure that we expose the cluster only to other parts of the cloud account, so we really want to make sure that we are using the right controls, and regulating that is something that RBAC by itself is insufficient. Pod security policies, for those who know or actually missed that, will not see the day of light in terms of GA. And presently, at least one element that is assumed to be replacing pod security policies is OPA, Open Policy Agent, and Gatekeeper, which by itself has some challenges because pod security policies are restrictive by nature, which means that if you deploy them, then it might break your cluster on one way, but on the other hand, you will be running in accordance to very strict policy profiles in terms of how your pods and containers are running. But on the other hand, if you go the OPA gatekeeper path, then you really need to manage pretty much discrete features and making sure that you apply those controls in an additive manner, which is quite different than how pod security policy works. But at the end of the day, if you think about it, our workloads or clusters never run with workloads that are not privileged. So some of the infrastructure components, for example, must run with some privileges with respect to the host itself, with some privileges with respect to the network, with some privileges with respect to the API server. And at the end of the day, this is something that we really want to make sure that we have well-established guardrails in terms of both understanding what are the risky parts, as well as enforcing those policies. Once we move into things like secrets, which has their own lifespan, which is different than the cluster itself, it becomes extremely challenging, and we want to revert to stuff that or components that help us manage secret lifecycle outside the cluster itself. So things like HashiCorp Vault or dynamic secret injection, or leveraging things like pod identity injection into the pod by components like, for example, IAM roles for AWS and EKS clusters, are really things that help us integrate our Kubernetes workloads in a way that kind of natively integrates with cloud services or cloud kind of offering that do not require to wire secrets in a weird way, or in a way that essentially can be bypassed. Network policies are an extremely important component. We will see that shortly when it comes to the CVEs. So what exactly happened as far as those security building blocks and the recent CVEs that were disclosed? So what we really see here is the trust boundaries of a typical Kubernetes environment, where we really want to make sure that the code that we bake into containers is something that we fully understand, like which are the source container image registries from which we pull images into the cluster, because this is kind of a threat vector that injecting kind of malicious images to our container image registry is something that eventually can land into our cloud account, our cluster worker nodes. And then from there, an attacker can actually start to manipulate the cluster and perform those lateral movements to obtain or get a hold of more valuable assets, and in the worst case, exfiltrate data from the cluster. But we really see several vulnerabilities that were disclosed. 2 of them are relevant to the control plane, to the management of Kubernetes, even in the event of the managed Kubernetes services, and 3 more vulnerabilities that are related to the worker node themselves. And let's take a deeper dive on that. So just to summarize, you really want to know what exactly you guys are trying to achieve as far as the security posture that you're building, as well as understanding your clusters. So for example, we know that in every cluster, we have infrastructure components, and we want to make sure that we account for them from a security perspective, in the sense that we know that they are supposed to run privilege. We know that they are supposed to be running, for example, like Prometheus or security agents. So we want to have a mechanism that enables us to kind of manage those exceptions in our environment. The second piece is, if you guys are running with multiple clusters, automating and regulating security across multiple clusters requires some unification of the security infrastructure that we want to implement. It's not straightforward to do that. If there is a difference between applications, that there are elements that are application specific, but if there are shared, for example, method for provisioning the cluster, that you can really share the security building blocks and policies and guardrails that you implement. Multi-cloud becomes extremely challenging. If you think about the C that covers the cloud aspect, clouds can be quite different than from one another, especially around the layers that configure the account, the credentials, the networking. Even though Kubernetes appears to be something that denormalizes or abstracts many of the cloud, the underlying cloud elements, there are still cloud-specific elements to Kubernetes itself. So again, multi-cloud becomes extremely challenging. As far as the security lifecycle of components that are running inside the cluster, for example, secrets, API keys, user identity, certificates, all of those needs to be well thought in terms of how we bring them into our applications. And when it comes to shifting left or the DevSecOps culture that we're trying to build, as far as bringing more security or delivering security through awareness and implementation that is already done in the development cycle. So you can really implement that in CI by leveraging open tools or commercial tools, which are quite powerful in that sense. So let's take a look, quickly look at what does it mean to scan our environment. So I have prepared here, and this is something that you can kind of register and create a nice dashboard for your environment. So I have here a little cluster that I created as part of for this webinar. It's a Kubernetes kind cluster. It's a single node, pretty simple. Doesn't do really much, but this is something that is based on Kubernetes version 18.2. And one of the things that you can achieve with a seed advisor, for example, is the ability to define scan policies. And specifically, I defined a policy that helps me identify which Kubernetes CVEs, the Kubernetes infrastructure CVEs, my Kubernetes kind cluster is presently vulnerable to. And you can really see that as part of the maintenance of the CVE, we can really flag which CVEs are presently running inside the cluster. Now, vulnerable doesn't mean exploitable, but it really means that presently the Kubernetes software version that I'm running in this specific environment is vulnerable to those following CVEs. And you can pretty much drill down into the individual details and really understand like what exactly is happening in terms of what this CVE is about, whether it's relevant to the control plane or the nodes. And essentially, when you try to think about vulnerabilities that are relevant to your cluster nodes, it's relatively harder to upgrade and maintain the nodes themselves. Pretty much if you're running stateful applications, it will take you longer to upgrade the underlying Kubernetes software, pretty much because you need to account for the data that is running there and make sure that you are rotating the nodes or doing kind of this rolling upgrade in a way that preserve the data. So you really need to kind of build your cluster in a way that helps you deal with those maintenance windows. So this is an example where a seed advisor our cloud SaaS can monitor your Kubernetes clusters for your CVEs. And naturally, you can define multiple scan profiles. For example, those that enables you to see, for example, port security analysis of your environment. And we'll see that down the road when we are talking about CVEs and how we can deal with that. So what are CVEs and why they are important and why everybody's talking about vulnerability scanning and what does it mean in the context of Kubernetes? So first off, CVE stands for the Common Vulnerabilities and Exposures. It's a database that basically allocates unique identifications for software issues that are normally disclosed by software vendors. Some of the software vendors that are out there has disclosure process, and some of them do not. But at the end of the day, this is something that pretty much tries to unify the way that we describe, identify, and understand the risk around our software components that we are running. Image vulnerability scanning talks about scanning the container images and understanding based on the OS packages that are baked into the container, or with some more advanced tools, you can actually do binary analysis. But at the end of the day, it does talk about the images that are supposed to be scheduled to be running inside the cluster. Kubernetes CVE scanning pretty much scans your Kubernetes components and helps you understand whether you are running with vulnerable Kubernetes software or not. So in the 4 to 6 weeks since I started to do the slides for this talk, there were 5 CVEs disclosed. The interesting part here, and I'm taking here a wild guess, that we will see 5, 6, so 8, 5, 5, 5, 6 disclosed at some point in time. The IDs that we see here do have a meaning, they're sequential in a way, but it looks like something is going to be released about it. That's kind of a guess. I don't know for sure. But at the end of the day, we had a couple of CVEs that talks about the control plane. And the basic idea around it is we want to make sure how or what is the risk or the blast radius that are associated with each and every vulnerability or weakness that we have in our environment. And we want to make sure that we can understand in terms of the blast radius, what are the components inside our cluster that may risk our environment in a way that someone can really exploit those vulnerabilities. So for example, the one that actually was disclosed last week talks about a pod that is able to inflict a denial of service. So essentially can take down the entire node while the Kubernetes control plane is not aware of the state of the node itself. So this is something that can be done with a pod that can mess, in quotes, with the storage of the node itself. And at the end of the day, if a pod, or if you're running workloads that are coming from an untrusted source, for example, take build systems, and if those build systems are running code that can manipulate the node, they can inflict a denial of service on a node and potentially on the entire cloud service that may be hosting that. So this is kind of one example of how we try to think about it. So one major issue that was disclosed a few weeks ago was really talking about man-in-the-middle attack where pods with enough privileges could have been send malicious traffic, or actually it's not malicious traffic, but it's traffic that at the end of the day is IPv6 router advertisement traffic, which basically confuses the forwarding place. So think about Calico, for example, which was vulnerable to this attack, or even the default Kubernetes CNI, which was vulnerable to this attack, confuses the underlying forwarding mechanism, the routing mechanism of your CNI, the container networking interface, in a way that the pod can get a hold of a traffic that is destined to the host or destined to neighboring pods. Now, the prerequisite for the attack is the ability to craft IPv6 traffic, and this is a very specific process level capability that requires an attacker to be able to mount such an attack. Mitigating the attack would kind of help us if we could have blocked any egress traffic from pods in a way that, you know, nobody can run IPv6 or inject traffic into our pods. Or for example, if we disable the very specific OS kernel feature that enables the support of IPv6 router advertisement. Now, if you try to think about it, why IPv6 is relevant to your clusters, if you are only using IPv4 and IPv6 is some sort of a legendary thing that everybody is talking about but not really implementing, well, the answer is that out of the box, Linux systems are equipped with a working stack of IPv6, and the fact that malicious pod or an attacker on the host is able essentially to mount this attack and get a hold of network traffic that is destined to neighboring pods by manipulating the underlying forwarding plane. So essentially, this is something that is relevant to your system. Now let's think about what exactly are the prerequisites. So for example, if we have a pod that is running on the host namespace, we really want to make sure that we do not allow it to do its those type of attacks. If you're running a privileged pod, this is something that we really want to make sure we cannot run. So at the end of the day, we're looking into something that is really required by having the ability to send traffic, raw traffic into the host. Another good example, a very recent one from last week, bypassing the localhost trust boundary. So again, this is a vulnerability in the way that Kubernetes provisions the host, the nodes themselves, pretty much related to kubeproxy and kubelet, which essentially an attacker can send a traffic from a neighboring pod or even from the host itself from a pod to the local host address. So that's 127.0.0.1. So even if you are sending that from a neighboring node, by manipulating the layer 2 addresses and the layer 3 addresses, you can really gain access to a process that is listening on a port on the local host from a remote host. So this is something that, for example, an application can make an assumption that no one can access a local or process that binds to a local host. And this vulnerability actually violates that. So if we look about, if we look into this vulnerability on a host, on a node, it was rated as 5.4. But if we are able to load a pod on the control plane, which is something that is possible with the non-managed Kubernetes services. So if you're not using EKS, but using COPS, for example, then loading a pod on the node and exploiting kind of the API server running with insecure port, which is off by default, but sometimes you can kind of change a default, you can really kind of take the entire cluster. So this is something that is rated as 8.8. So if you think about how can you know whether you are vulnerable or not, this is something that you really need to make sure, for example, that you don't have pods that are able to send traffic into the network. And if you have pods that has those toleration that enables them to run on the control plane, that's again something that you want to avoid. So at the end of the day, we really want to understand the blast radius. So let's take another example. This is a CVE that is related to the Kubernetes control plane. So the interesting part before we are diving into this, the details of that, this is something that is relevant to some extensible parts of Kubernetes, specifically around storage class. And the interesting part that you can see that with definition of the storage class, you can see that on the parameters, you have a parameter that says REST URL, which kind of gives us a hint that Kubernetes, by way of the implementation, is actually activating this URL. So as far as rating goes, On the non-managed Kubernetes, it was rated as 6.3. Effectively, the vulnerability basically enables an attacker, so someone that can run kube control command to extract data from the API server. And specifically, the vulnerable component is the cloud controller manager. So this is the glue layer, the cloud-specific Kubernetes component that helps Kubernetes kind of stay cloud agnostic. So cloud controller manager is actually the component that implements cloud-specific calls to implement, for example, services of type load balancer, to provision storage, and other resources that are cloud-specific. So one point to actually note as far as the disclosure timeline. So when we really think about, yeah, those CVEs are coming and going pretty much quite often, it's not really the case with Kubernetes, at least recently. The positive thing about those recent disclosures is that Kubernetes becomes more and more popular software, and more security researchers are actually looking into the software and manipulating the software in a way that those weaknesses are discovered. But the mind-blowing fact is that on December 6th, 2019, Microsoft Research Center was actually had a submission around this specific vulnerability. So that's more than 6 months ago. And you can see that Kubernetes Security Committee requested an embargo. So normally kind of the disclosure process, you can see that from discovery, or actually from disclosure to a fix, is something that took significant amount of time. And if you think about it from a public disclosure, from actually Kubernetes releasing the patches, it also takes time to apply those patches to your environment. So at the end of the day, if you think about all of those CVEs, it necessarily means that your systems were running vulnerable for many, many, many months. So effectively, CVEs are almost kind of, or in some cases can be those post-mortem fixes or remediation that we apply to our system. And our systems may have been exploited or abused by those CVEs if they are not kind of disclosed or patched. So there is a very wide time window that normally CVEs can be exploited by the systems. And you really need to ask yourselves, like, what are the non-Kubernetes native security controls that help you deal with figuring out, for example, if those weaknesses are being exploited inside your environment. So again, going back to my example here, if I am, for example, need to understand if someone is running with capabilities that enables, for example, a pod to send traffic into the network. So I can really go to my dashboard and build a profile that help me analyze the CVEs. So unlike OPA, for example, that runs as an admission control, here I can scan my existing state of my cluster. So whether this is something that actually went beyond my OPA gatekeeper, or even I didn't have OPA gatekeeper, and I can drill down to specific pods that are running inside the system. And I can, even beyond that, I can really see, for example, like which capabilities are being used by pods that are running inside my cluster. So for example, this is the permission that enables me to mount the network attacks. So bypassing the localhost boundaries, or for example, messing up with the IPv6 router advertisement. So this is an example where I can explicitly understand risk and blast radius. And if I feel that this is something that is by design and it's not exploitable, I can really say, okay, this is something I well understand. I can exclude that from my scan results, and I don't need to further dig in. And understand kind of the risk associated with that. So again, the ability to analyze our configuration helps us to reduce dramatically the blast radius of our clusters and environments in general. So going back to the slides. So what really happened with the server-side request forgery? So let's track this, because this is something that actually I want to highlight, something that is related to how we monitor the Kubernetes API server and what is the important behind Kubernetes Audit Log. So as we saw earlier, the weakness or the vulnerability is related to the fact that once we deploy storage classes from a very specific kind, which is GlusterFS and a couple of more, whether you're using this type of storage or not, it's not really important. The Kubernetes API server, so an attacker, so think about me as a user typing kubectl apply, a YAML file that contains this storage class. It's getting deployed to the API server. The API server will turn this request to the Cloud Controller Manager, the cloud glue layer of Kubernetes. And in a way, if I place in the REST URL that we saw earlier, an attacker server that I can control, I can respond with a HTTP redirect, which basically, because of a weakness that happens in the Go HTTP client and the way that the Cloud Controller Manager implements, I can send an HTTP redirect, which will make the Cloud Controller Manager make a call of my discretion. Specifically, if this is a managed Kubernetes service, I can call to the underlying cloud provider perimeter. So think about it, you can perform HTTP calls inside the managed Kubernetes environment of your EKS, GKE, and extract stuff from the metadata API server or do other elements. And the data that returns, or some of it, will be returned to the user that actually performed those events. If you really see kind of the action that we see here, we create resource of certain type, we get events, and in order to mount an exploit, we really need to kind of invoke those commands in a quite frequent manner, which means that if we monitor the Kubernetes API server logs or the audit logs, we can really differ from those logs that actually something anomalous happens in the system, which brings me to the last topic I have for this webinar. So every Kubernetes API server keeps an audit trail or an audit log. So think about it as like CloudTrail. Every API invocation made by human users like kubectl or even your cloud dashboard is logged, and it's saved normally into kind of persistent storage that external systems can actually stream and analyze those streams and defer insights about the system in terms of those logs. So for example, we can detect known and unknown vulnerabilities in the Kubernetes API server because of the way that the Kubernetes API server is being accessed or APIs are being invoked. Or for example, if we are going back to the example of Twitter and the social engineering, if we have users that someone breached into their laptops and now they are starting to perform those API server calls using kubectl or directly or whatever, or even from the node itself, we can really detect those anomalies because we are tracking users and we are tracking how resources are being accessed, and all of those moving parts is something that the Kubernetes Audit Log pretty much represents a gold mine from a security perspective. We can even detect RBAC misconfiguration. So for example, if we see a spike or an increase of permission denied after we deploy a new software version, one of the root causes for that may be misconfigured or not aligned, or RBAC policy is not aligned with the application functionality. Another actually good example that one can leverage as far as the Kubernetes Audit Log, you can place rules that says, for example, if someone exec into a pod in a production cluster, we can really send an alert to the team. So it really gives us the ability to both plug analysis and hunting for anomalous behavior, as well as placing policies that helps us kind of regulate how Kubernetes cluster is being utilized. So when we kind of think about all of those use cases, having something that is more of kind of both policy driven and AI driven helps us leverage the Kubernetes Audit Log to detect the CVE that is associated, for example, with storage class. So let's take that as an example. If an attacker starts to deploy storage class and create persistent volume claims of this vulnerable storage class, so an increase or an unexpected increase of those API invocations is something that threshold-based approach can help us, but the problem is that we really don't know beforehand which are the vulnerable APIs are there, or how exploits are actually being exploited, or how vulnerabilities and weaknesses are being exploited by an attacker, which means that having something that is more of adaptive, that learns how resources and users and service accounts activate the Kubernetes APIs is something that can help us detect that. So with that in mind, let me show you an example of what a system like that can perform. So while the system loads, we can really see here an example of a timeline that tells us a story. So I can zoom in, for example, on a couple of assets. I can investigate those specific users. But more importantly, I can, for example, see that these specific users, which are unauthenticated users in the environment, actually performed API access to the Kubernetes API server and got permission denied. If I want to have a look on, for example, which type of namespaces they were trying to access, we can see that those assets actually were able to access, or trying to access, all the namespaces in the environment. If you want to see, for example, the origin of those users, I can pretty much visualize those elements. So at the end of the day, the ability to understand, for example, if we're taking, again, the example of the cloud storage vulnerability, we can, for example, see resource type, and we can see which resource types are being employed inside my environment. So I don't see here, for example, storage class. So this is an indication that helps you understand that this specific exploit was not applied into the system based on the fact that we don't have a record of those storage class and PVC creation attempts. So with that in mind, I think it pretty much wraps up the technical content I wanted to share. And I wanted to encourage you to whether you guys want to use some of our open source and open tools on GitHub that would enable you to perform CI scan, understand, for example, analyzing your RBAC, or you want to take our cloud service for a spin and analyze your Kubernetes clusters for CVEs, or even try Kubernetes Audit Log Analyzer, which is our CDK audit. Hit those links and we're happy to kind of take it for a deeper spin. And with that in mind, I think we can move into the Q&A part.
Awesome. Thanks so much for a great presentation. It looks like we have one question here. It's from Jin Dong, and it says, in the clusters FS REST API example, traffic to outside Kubernetes should be controlled?
Should be? What was the last?
Yeah, should it be controlled?
And this is in the context of the control plane vulnerability?
I believe so. Let me see. Hold on. I think they might be controlled. Yes.
Yeah. So essentially, yes, the general idea is that the control plane, even in the managed Kubernetes cloud instance, it should be controlled. But going back to the beginning of this webinar, if we are provisioning our Kubernetes cluster with a publicly facing API server, so when you provision clusters, you can actually do private clusters or you can do public clusters. So if you are using the managed Kubernetes option with a public cluster, the control plane can actually connect from the cluster to the internet, which means that an attacker can still manipulate a server that is running on the outside and with those redirects that I showed earlier. So it really boils down to how you provision. The best practice is provision private clusters that prevent the control plane from accessing the outside world. And the same goes for clusters that are running in private VPC.
Great. Okay, let's give folks another minute. A reminder, if you have a question, feel free to drop it in the Q&A box at the bottom of your screen. We'll give folks just a few moments here. Okay, well, I think that is all the questions that we had for today. Thank you again, Gadi, for a great presentation. And thanks again to everyone for joining us. Just a reminder that the webinar recording and slides will be posted later today to the CNCF website. We look forward to seeing you at a future CNCF webinar and hopefully KubeCon virtual here in a couple weeks. Have a great day and thanks everyone.
Thank you.